Hey, calculus, we are on to the indefinite integral. So I'm going to start this page by kind of talking about this in general, and then we'll formalize it in a minute. The first question is to find the antiderivative of f of x is equal to 0. So first I want to say the integral of f of x would be the antiderivative, and this is equal to some new function, specifically because this is an antiderivative. If I take the derivative of that thing, I'm going to get what I have. So the question is, what function has a derivative of 0? Now your answers can vary. Let's say you said 100. You're correct. The derivative of 100 is 0. But you could have also said negative 18. Or you could have said f of x is equal to negative 0.003. The point is, this function would have had to have been a constant for its derivative to have been 0. Okay. So now let's think about this a little bit more. What about a function, f of x is equal to 5? What's the antiderivative of 5? Well, if you said 5x, you're correct, but this is not the only solution. If you said 5x plus 2. Hey, the derivative of that, f prime of x, would be 5. Derivative of 5x is 5, and the derivative of 2 is 0. So that works. You could also say f of x is 5x minus 11. Or really, one final answer, the f of x is equal to 5x plus c, where c stands for, a constant. So then the question is, can we generalize it for any number k? And the answer would be yes, of course. The antiderivative of some function is equal to f of x, and specifically, in this case, would be kx plus c, plus this constant, right? Because if I take a derivative of a constant, it's 0, so I don't necessarily know it's there just with the antiderivative. Let's then use this to revamp a little bit our polynomial antiderivative formula, or that what we talked about the other day, our power rule for antiderivatives. So we had said, if a function now, if f of x is equal to k, some coefficient times, k times x to the nth power, then the antiderivative of this function, we are going to call capital F of x, is, I'm going to move this down here, is, well, we have x to the n plus 1 all over n plus 1. But we still have that coefficient of k. And now what I'm saying is we're going to add a plus c, plus a constant. Because this is what we're talking about when I say an indefinite integral. Indefinite means we don't have bounds. So we're looking at something called a family of functions. It could be any function here. So let's continue to think about this. When won't this work? When will this not work? Specifically, when is this formula going to have an issue? Well, it's going to have an issue if we divide by 0. So we're going to have a problem when n is equal to negative 1. Because in that case, we would have x to the negative 1 plus 1 all over negative 1 plus 1 which is really x to the 0, which is fine, but we're dividing by 0, and that's an issue. What function are we talking about then? We're really talking about a function that looks like this. A function we all know and love, x to the negative 1, or 1 over x. So now the question is, what function has a derivative that's 1 over x? Think about it for a second. The antiderivative of f of x with respect to x, or the antiderivative of 1 over x with respect to x. This is the natural log of x, and we still technically need that plus c. Because, again, the derivative, let's say our function is the natural log of x. We know this. We've done this a couple times. The derivative of that is 1 over x. Oops, I kind of meant to go here. And an antiderivative is going the opposite way. Now, if you didn't quite follow that, that's okay. This next slide is going to give us the most basic functions that you would technically need to know in their antiderivative. So here's our function. On the right, I'm going to write the antiderivative. Or again, remember the integral of a function with respect to x. We are saying the antiderivative, we are denoting it with a big capital F of x. So the antiderivative of 1 over x, capital F of x, we just said this one, is the natural log of x plus a constant. What is the antiderivative of e to the x? Well, this one's a nice one. It's just e to the x, right? Because the derivative of e to the x is itself, and so hopefully it makes sense that the antiderivative of e to the x would also have to be itself. What about sine of x? We talked about this way before you guys left for vocare, but the antiderivative of sine is negative cosine of x. We're going to add that plus c. The antiderivative of cosine is sine of x. And we're going to add a plus c. And in this one, I'm giving you a little trick here. 1 over cosine squared is really secant squared of x. So that means the antiderivative would be tangent of x, of course, plus c. This is a page you will be expected to know, though really just take good notes because you get to use your notes on tests and quizzes. I'm going to go to the next slide very briefly. You can pause if you need. Here are 2 reminders of things we know to be true. The antiderivative of a function plus another function is the same as the antiderivative of the first plus or minus the antiderivative of a second. We also know that if I have a coefficient, I can just bring it out front and multiply it in, just like my derivative rules. So if you need to pause this to write it down, please do. But then we're going to do an example together. Here's my example. It's a long, ugly, scary-looking function, but don't stress. It's not as bad as you think. They want us to find the antiderivative of sine of x plus 3 times cosine of x minus x to the negative 1 plus 7x squared with respect to x. Take it piece by piece. Find the antiderivative of the first, then find the antiderivative of the second, and keep going. Try it. Because I'm going to put the solution up now. So the antiderivative of sine is negative cosine of x plus c. That's this first one. The antiderivative of cosine of x would be sine of x plus c, but then I have that 3, so I can multiply that 3 out front. The antiderivative of x to the negative 1 is the natural log of x plus c. This would be minus because of this coefficient. And then, last but not least, we have plus 7 thirds x cubed plus c. And while this is is a correct answer. Notice we have a lot of plus c's. We're adding a lot of different constants. Technically, all of those are just a constant, a number. So I can add them all together to get a new constant. We don't really need the plus c after each of those. So my final answer would be negative cosine of x plus 3 sine of x minus the natural log of x plus 7/3 x cubed plus c. We're basically combining all of these coefficients into, one coefficient at the end. I'm going to skip this next example, and we're going to talk about one others. If a function is equal to 2 plus 4x plus 5x squared, find an antiderivative such that the antiderivative at 1 is equal to 5. So we start by finding an antiderivative. F of x is equal to 2x plus 4x squared over 2, we can simplify in a second, plus 5x cubed over 3 plus c. This is what we need to change. We need to figure out what this coefficient would be so that when I plug in 1, I get out 5. So what do? I use this information in my formula here. I really would put 5 is equal to 2 times 1 plus, I'm going to simplify this, so 2 times 1 squared plus 5 times 1 cubed all over 3 plus c, and my goal is to solve for c. 2 times 1 is 2 plus 2 plus 5/3 plus c. It's all equal to 5. When I move my things over and I do a little simplification, I solve and I get c is equal to negative 2/3, meaning my final answer, the actual function, because there's technically an infinite amount of functions who have a derivative 2 plus 4x plus 5x squared, but the actual function, the specific one we're looking for, would be 2x plus 2x squared plus 5/3 x cubed minus 2/3. We're finding the one and only. All right, check the homework online, and I will talk to you.